In this example problem, we are told we have a complicated object, but this complicated object is the combination of several simple objects. We have a cylinder that has a thin spherical shell on top of it. We are given the mass and radius of the shell and the cylinder, and we're told on the outer face of the cylinder there are two small point masses. We're asked to find the moment of inertia of this complicated object. We're asked to find the kinetic energy of rotation when we're given an angular velocity for this object. But first we're asked, does it matter where the point masses are glued? In other words, if I imagine here's my cylinder, here's my shell, and they are spinning or rotating about a central axis, will I get one moment of inertia if I place the point masses here? Will I get a different moment of inertia if I place the point masses, say, here and here? Pause the video, think about it, come back with an answer, and think about what your reasoning is. So the answer to this question is it will not matter where we glue the point masses. As long as they're glued on the outer face of the cylinder, we will always get the same moment of inertia. What is our argument for that? Well, before we actively defend that statement, let's first think about what this equation means. In its most general form, the moment of inertia in this course is written as the sum over mr squared. So what is m, what is r, and what are we summing over? To help us think about this scenario, for the moment, let's ignore this more complicated object and let's consider a simple physical setup of only 3 particles. If we only have 3 particles in a system, it's easy to keep track of everything. So we'll say here is the location of particle number 1, here's the location of particle number 2, and here's the location of particle number 3. Let's also suppose that these 3 particles are all moving in a circular path about some common center of rotation. So you could kind of think of it as though they're all in circular orbits about some common central point. And we'll say their center of rotation is right here. Now, from looking at this picture and the way it's drawn, I could see that particle 3 is the closest particle to the central point. Particle 1 is the furthest particle from that central point of rotation. So I could say particle 1 lies at a distance r1 from that central point. Particle 2 lies at a distance r2 from that central point. And particle 3 lies at a distance r3 from that central point. The total moment of inertia of the entire system, I'm not asking about the moment of inertia of a particle. I'm asking about the moment of inertia of this system of particles, all of them combined, is going to be the moment of inertia of particle 1 plus the moment of inertia of particle 2 plus the moment of inertia of particle 3. That's the summation term I have up here. So I would write the moment of inertia of my entire system, which is basically saying I total, is equal to the mass of particle 1 times the distance from particle 1 to the center of rotation squared, plus the mass of particle 2 times the distance from particle 2 to the center of rotation squared, plus the mass of particle 3 times the distance from particle 3 to the center of rotation squared. At this point, I have accounted for every particle that makes up my system, so I could plug in M1, M2, M3, R1, R2, and R3, put in a calculator, and be done. I found the total moment of inertia of the system of 3 particles. But you might want to say, the cylinder, it has a mass of 4 kilograms, and the shell has a mass of ½ kilogram. We're looking at Avogadro's number of atoms that make up these objects. We can't realistically add up Avogadro's number of terms. Well, that is true. But let's write out all the particles in the cylinder and the shell and find their moment of inertia. We're not going to actually write out every term, we'll just do it symbolically. To do that, I am going to say the total moment of inertia of every object in this contraption is I total equals, first I'll add up the moment of inertia for every atom that makes up the cylinder. There's going to be a lot of them, but we're only doing it symbolically. Mass of atom number 1 in the cylinder, the distance of atom number 1 to the center of the axis of rotation squared, plus the mass of atom number 2 in the cylinder, the distance from atom number 2 to the center of the axis of rotation squared, and add that for every atom in the cylinder. I have a subscript 1, 2, 3, and so on, designating which atom I'm talking about, and I have a subscript C designating I'm talking about the atoms in the cylinder as opposed to the thin spherical shell. I write out all of these contributions. I accounted for every atom in the cylinder. Now I'll start writing out the contribution of every atom in the thin spherical shell. I'm going to leave a little space here because I'll write underneath that shortly. So I could write plus, because we're adding every atom in the entire contraption, the mass of atom number 1 in the shell, the distance atom number 1 in the shell is from the center of the axis of rotation, plus the mass of atom number 2 in the shell, the distance atom number 2 is from the center of rotation squared. I add up every term there. And I have now accounted for every atom that makes up the thin spherical shell. There are 2 more particles I have yet to account for. I did not account for these 2 point particles that we glued on the outer surface of the cylinder. We accounted for every atom in the cylinder, that is this first line. We accounted for every atom in the thin spherical shell. So let's ask a question. What will the moment of inertia of these 2 small point particles be? Well, when I calculate moment of inertia, m is the mass of the particle I'm considering. We know the mass of these 2 small point particles. That was given in the problem. How far away are these 2 small point particles from the center of rotation? Well, if the center of rotation goes right through the central axis of the cylinder, and the point particles are on the outer face of the cylinder, then the distance from the point particle to the central axis of rotation will be the same as the radius of the cylinder. And that will not matter no matter where I glue the point particle on the outer face of the cylinder. The point particles will always be a distance from the center of rotation equal to the radius of the cylinder. So I could write then plus mass of point particle A, MA, RA squared, plus the mass of point particle B times the distance from point particle B to the center of rotation. Now, RA and RB, the distance from the point particles to the central axis of rotation will be the same as the radius of the cylinder. I'm just writing it symbolically here just because. If I look at what I've written here, this term here accounts for every atom in the cylinder. So I could think of this as just being the total moment of inertia of the cylinder. And this term here is every atom that makes up the thin spherical shell. So I could think of this entire sum as the moment of inertia of the shell. And then I still have my 2 point particles, but it's easy to handle a point particle. I'm not going to really write it any differently. So I could write the total moment of inertia of this system of a complicated object as the moment of inertia of a cylinder plus the moment of inertia of a shell plus the moment of inertia of particle A plus the moment of inertia of particle B. Because both particles were chosen to have the same mass and they're both at the same distance from the center of rotation, it doesn't really matter which particle I call A and B. So I'll call this particle B and I'll call this particle A. just because I can. Okay, particle A and particle B, that is going to be easy to work with. The moment of inertia for a point particle is mr squared. The moment of inertia for a cylinder, well, I don't know what that is, so I go to the textbook, look up a solid cylinder, and I get that the moment of inertia for a cylinder is 1/2 mr squared. So moment of inertia for a cylinder is equal to 1/2 big M times big R squared. And here, big M is the total mass of the cylinder, big R is the radius of the cylinder. And similarly, the moment of inertia for a thin spherical shell is equal to 2/3 big M times R squared. For this equation, big M is the mass of the thin spherical shell, and big R is the radius of the thin spherical shell. In general, this mass does not need to be the same as this mass. The cylinder does not need to have the same mass as the shell. Similarly, this radius does not need to be the same as this radius. In general, the cylinder and the shell could have different radii. In this particular example, we chose that the cylinder and the shell will have the same radius, but they have different masses. So I could calculate each of these terms out individually. If you're curious, where do these prefactors of 1/2 and 2/3, and if you look at some other terms, where do these other terms come from? Well, the thing is, the way we would calculate 1/2 mr squared is you would treat the cylinder as a solid object of uniform density. So even though atoms are point particles, you pretend all the mass of the cylinder is perfectly smeared out over the entire volume of the cylinder. And you would turn this sum into an integral. You would integrate over the entire volume of the cylinder. And when you go through that 3D integral, you end up with some prefactors that come out from your integration. So that's where these prefactors, these fractions come from. However, you don't need to do that. You just need to go to the table in the textbook and look up the value of the moment of inertia of a cylinder and the moment of inertia of a shell or any other object you might encounter. So I would say that for this problem, the moment of inertia of the cylinder I'm dealing with is 1/2 times the mass of the cylinder I have, which is 4 kilograms, times the radius of the cylinder squared, which is 0.2 squared. If I put these numbers in a calculator, I get the moment of inertia of my cylinder is 0.080. For my thin spherical shell, I would say the moment of inertia of my shell is 2/3 times the mass of my shell, which in this problem is 0.5, times the radius of the shell squared. In this case, the radius of the shell happens to be the same as the radius of the cylinder, so I'll again have 0.2 squared. If I put these numbers in a calculator, I find that the moment of inertia of my thin spherical shell is 0.013. Now I accounted for the cylinder and the shell. I still need to account for the moment of inertia of point particle A and point particle B. So I could say the moment of inertia for point particle A is just going to be mr squared because it is treated as a point particle. I'm essentially treating particle A as a single atom, and in many cases that could be a good enough approximation. So I'll have mr squared. The mass of particle A is 0.2 kilograms. The distance that particle A is from the center of rotation is the same as the radius of the cylinder, so that would be 0.2. So coincidentally, I have 0.2 times 0.2 squared, and when I put these numbers in a calculator, I get 0.016 for particle A, and particle B in this problem has all the same numbers, so I don't need to go through this calculation again. It would be all the same. Particle B will have a moment of inertia of 0.016. The total moment of inertia will just be the sum of these four terms. So I could say the total moment of inertia for This contraption of a cylinder and a thin shell and 2-point particles glued to the outside edge is going to be 0.080, the moment of inertia of the cylinder, plus 0.013, the moment of inertia of the thin spherical shell, plus 0.016, the moment of inertia of point particle A, plus 0.016, the moment of inertia of point particle B. I add these four contributions together and I get the total moment of inertia for this complicated thing is 0.125. What units would moment of inertia be in? Looking at the equation for moment of inertia, m mass, that's measured in kilograms, r is a distance that's measured in meters. So the units of moment of inertia are kilogram meter squared. And there is no special name for the units of moment of inertia. It just is kilogram meter squared. In part C of this problem, we are told that this thing is spinning at a rate of 5 revolutions per second, and we're asked to find the rotational kinetic energy. To do that, I will say the rotational kinetic energy of an object is given by kinetic energy of rotation equals 1/2 I omega squared. Whenever we work with this equation, our angular velocity omega must always be in units of radians per second. We are told this contraption is spinning at a rate of 5 revolutions per second, so we need to convert that. I could say omega equals 5 revolutions per second. I'll multiply this term by 2 pi radians over 1 revolution. And when I perform this conversion, I get the angular velocity of this object is 10 pi radians per second. If I want, I could multiply 10 times pi. I would get 31.4 radians per second. I don't think it's that important. As long as you have the correct term plugged in for omega, you'll be okay, whether you choose to write it like 31.4 or if you choose to write it as 10 pi. So I could say the kinetic energy of rotation for this object is going to be 1/2 times 0.125, the moment of inertia, times the angular velocity squared, 31.4 squared. And when I put this in a calculator, I find the kinetic energy of rotation is going to be 61.7. Because we are dealing with energy, the units of this will be joules.